Hello, it's me, Christian, and my partner was Kai, and this is our bridge project presentation. Okay, so let me scooch out of the way here. Okay, cool. So our research process consisted of like hours of very in-depth research,
It was, like, 20 minutes, let's be real.
and our whole goal was to basically find the most efficient possible bridge.
Quality over effort.
So we stumbled upon three different types of bridge, which were the beams, the truss bridges, and the suspension bridges. The beam bridges didn't really seem super reliable because it required like stuff to be underneath it in order to like support the bridge. The suspension bridge didn't seem super viable because we would need materials that could have tension and materials that would like bend a bit more so we finally landed on truss, which is good for solid and we don't need to have bottom supports. Um and then the two different types of truss bridges we found were the Pratt and the Howe bridges. We decided that we would use a mixture of both. So we would basically use the Pratt style for our side where we have the slashes, and then we'd use the Howe style or the X's for the bottom, because we thought the bottom would need force more evenly spread, and the Pratt would want maximum focus on keeping the walls together and making sure that we didn't have the top breaking because the top was a lot weaker than the bottom.
All right, so for the physics concepts displayed in our bridge, the first one we have forces and force distributions. Um, and this is displayed by the downward force created by the bridge breaker and how the bridge distributes that force to all of its joints and toothpicks in the structure. The next concept was tension, and a lot of our trusses were tension trusses in the sense that the forces acting on them and distributing the downward force were tension forces, and these can be seen in red in our diagram to the right. In opposition to these tension forces, we have compression forces, which is similar to uh, the spring stuff we did earlier in the year. And these are seen in green on the diagram to the right. And the total compression forces are equivalent to the total tension forces when the bridge is still standing. And as more force is added downward, both the tension and the compression forces increase, so they cancel each other out, and we don't have one overpowering the other and breaking. When our bridge finally did break, it was one of the top beams that gave in, and this means that the tension forces were greater than the compression forces, and that led to one of the compression beams on top breaking. Okay, so for our construction and materials, we did a similar thing to a lot of other groups in the sense that we started by laying out all our toothpicks on a flat table and gluing together our side pieces. And once those dried, we were able to stand them upright using a bit of support from tape and connected the two side pieces with crosses, so we had a fully upright standing bridge. And once we let that dry, it was pretty much ready to go. However, we did have to make some modifications along the way, as everything didn't go as planned. The first thing that happened is instead of having 6 different segments with diagonal beams, we only had 5. So we had one middle segment instead of having 2 middle segments. So we made this one a cross with 2 diagonals rather than just one diagonal. So it'd be even support in both directions. And then because we did this, we were struggling to make sure the bridge spanned the whole gap of the bridge breaker. So we had to add these little extensions to make sure we were able to be long enough. And then we also cut off some toothpick ends from the top and some glue pieces, which were just extra weight that wasn't adding anything to the structural support of the bridge.
All right, fantastic. And now time to move on to our efficiency. So efficiency is really easily calculated. You basically just take the weight and you divide that by the weight of the bridge in grams, and that gives you this number, which was second best in the class, so it was pretty good. Okay, so one of the main reasons we think our bridge is so efficient is because we had a lot of glue. We had a very messy bridge, and wood glue is a lot stronger than toothpicks. So that's why we think our bridge was able to hold so much while still being so light. So yeah, I guess if we were to do this in the future, one of the main things we'd focus on doing is adding more wood glue all over the bridge, maybe making a mold and making it purely out of wood glue in order to maximize the amount of wood glue we have, since that was by far our strongest and lightest part of the bridge.